Welcome to Wildcat Science with Mrs. Haugo. This is Physical Science, Chapter 1, Forces, and today we're working on 1.7, Newton's third law. Please find your book and open it up to page 16 to follow along. So in experiment 1.5, sliding friction, you will realize when you begin to pull on the block with the spring scale, the block will not move. The frictional force exerted by the table on the block balanced the force exerted by the spring. Does the block always exert a frictional force on the table? If so, how big was that force? You can see with the frictional block and the spring scale, as I am pulling it, the spring scale would pull a little bit before the block would move. So the block did exert a frictional force on the table, and the question is, how big is that force? So if a frictional force exerted by the pulled block could move the table, we could balance this force using another spring scale. This would tell us how large the frictional force is. Obviously, the table stays put without the force provided by an additional spring scale, so we can't answer this question. However, suppose we put the block on a light cart. The wheels on the cart, which cannot be seen in the photograph below, have very good bearings. As a result, there is very little friction between the cart and the table. If we now pull on the block, the cart will move with the block. To keep the cart at rest, the frictional force exerted by the block on the cart must be balanced by another force. Pulling with the second spring scale provides this balancing force. So let's take a look at this picture. So we have our block and we're pulling it with a spring scale. And then this cart can move. And then we're balancing it with another spring scale so that the block and the cart don't move. If you look carefully, these spring scales are being pulled with the same force. It looks like 1, 2, 3, 4, 5 newtons. Note in figure 110 that the cart is pulled to the left. The cart's being pulled to the left and the block is pulled to the right. Let's call the force exerted by the spring on the cart as force A, and the force exerted by the spring on the block, force D. And we can see that they are equal because they are equal in strength. And then figure 110 is a block on a cart. It has special wheels. There's very little friction. All three objects are at rest. The cart is pulled to the left and the block is pulled to the right. And the reading on both spring scales are the same. Okay, please take a moment and do a digital post-it note. Looking on page 17, figure 111, the top one, A, the force is acting on the cart. So A is the force of the spring scale on the cart, and B is the force of the block on the cart. And then looking at B, the force is acting on the block. So D is the force of the spring scale on the block, and C is the force of the cart on the block. So now concentrate on the forces acting on the cart. The spring pulls the cart to the left with a force A. The force of friction exerted by the block pulls the cart to the right with a force B. So the force of friction on the block is pulling the cart to the right. Since the cart is at rest, these two forces must balance each other. A is equal to B. Force A is equal to force B. We now apply the same reasoning to the forces acting on the block. The spring pulls the block to the right with a force D. The spring is pulling on the block with force D. The force of friction exerted by the cart pulls the block to the left with a force C. So the force of friction between the block and the cart pulls the block to the left with force C. Since the block is at rest, these two forces balance. D is equal to C. We can now substitute B for A and C for D in the first equation, and we conclude that B equals C. In other words, the strength of the frictional force exerted by the block on the cart equals the strength of the frictional force exerted by the cart on the block. These two forces act, of course, in opposite directions. So let's look here. The force of friction on the cart by the block is equal to the force of friction by the block on the cart. In words, the strength of the frictional force exerted by the block on the cart equals the strength of the frictional force exerted by the cart on the block. These two forces, of course, are in opposite directions. Now consider another situation. In experiment 1.4, the magnetic force, you measured the force that the lower magnet exerted on an upper magnet. During the experiment, you had to hold the lower magnet in place. Clearly, the upper magnet also exerted a force on the lower magnet. Were the two forces equally strong? You cannot tell on the basis of the experiment. Experiment 1.4, because you held the lower magnet down with your hand. However, many experiments have shown that the forces that two magnets exert on each other are equal in strength and opposite in direction. Please take a moment and do a digital post-it note. So you can see in experiment 1.4, we're going to have a magnet and then a lower magnet, and we're going to figure out the force needed to separate the magnets. So we're going to figure out the magnetic force. Finally, let us consider another type of force. The weight of a rock on the surface of the earth is the force with which the earth pulls the rock down. This force is called the gravitational force. Does the rock pull the earth up with an equal force? No experiment you can do in the lab can detect the effect of the gravitational force that the rock exerts on the earth. To see why this is so, consider the following. If the forces on the friction block do not balance, the block would start moving. If the forces on the upper magnet did not balance, the magnet would start moving. However, in the case of the earth, we would not detect any motion because we would be moving right along with the earth. Nevertheless, studies of the motions of the earth and the moon show that the gravitational forces that the earth and the moon exert on each other are equal in strength. In fact, all forces known today that act between two objects along the line that connects them are equal and opposite. This property of the forces is known as Newton's third law. Newton's third law may appear strange to you. Is it possible that when a heavy truck collides with a small car, the forces acting between them are equal and opposite? Equal forces does not always mean the effects of the forces are equal. Obviously, the small car may be completely destroyed, whereas the truck may suffer only minor damage. Newton's third law relates only to forces, not to their effects. So if you have a big truck and a little car, and they hit each other, the forces exerted on each other are the same. However, the effects of the force on the big truck, from the big truck on the little car, are not going to be the same as the effects of the force of the little car on the big truck. Now that we've finished reading, we are going to take notes. Please find your binder and open it up to the table of contents. Please enter 1.7 Newton's third law, and then you can continue on the same page as 1.6. Just make sure to skip 3 lines. So please go to that page, skip 3 lines, and title it Chapter 1.7 Newton's third law. So Newton's third law states, for every force there is an equal and opposite force, which means forces come in pairs and that forces act on different objects. So let's take a minute and talk about what that means. So please make this diagram in your notes. you have a cart, and you can probably draw a nicer one than me, and then a nice block, and then we have forces C going to the left and force B going to the right. So B is the force of friction exerted by the block on the cart going to the right, and C is the force of friction exerted by the cart on the block. So for every force, there's an equal and opposite force. So for force B, force C is going to be equal, and you can see that it is opposite. And the forces always come in pairs. You can't have force B without force C. And another important thing is that they are on different objects. B is the force exerted on the cart, and C is the force exerted on the block. If they weren't on different objects, nothing would ever move, so that's an important point also. Newton's third law doesn't just apply to frictional forces, it applies to all forces. So please write this down also. So obviously the force of friction, and that's the example above. Magnetic force, which we're going to see in our experiment. So we have the force of the lower magnet on the upper magnet is equal and opposite to the force of the upper magnet on the lower magnet. So the force exerted by the upper magnet on the lower magnet is equal and opposite to the magnetic force exerted by the lower magnet on the upper magnet. And we know that the magnetic force is greater than the weight of this block because it holds it up. So please write this down. The force exerted on the upper magnet by the lower magnet is equal and opposite to the force exerted by the lower magnet on the lower magnet by the upper magnet. Newton's third law also applies to the gravitational force. Please make this drawing of a rock on Earth, clearly not to scale, but the force of gravity from the Earth exerted on the rock is going to be equal and opposite to the force of the Earth, of the rock on the Earth, the force of gravity on the rock pulling up on the Earth. The effects are not the same. The force exerted by the Earth on the rock is equal and opposite to the force exerted by the rock on the Earth. Please write that down. Even though the forces are the same, the effects of the two equal forces are not always the same. For example, and please write this down, the force of gravity on me keeps me on the Earth. The force of gravity on Earth exerted by me doesn't actually do anything. And another example, a semi hits a smart car, a little smart car, and the forces are the same, but the effects on the smart car are much greater. So the forces are equal, but the effects are not necessarily equal. So that concludes our 1.7 reading and notes. Good job today.